morning, everybody. Nice to see a lot of people. My name is Tonnie Telgenhof Oude Koehorst, working at Nedap in the Netherlands. A little bit just started about 40 years ago. So I have some knowledge in that area, and I'm responsible for the global sales of UV drivers, low pressure, medium pressure, even LEDs if you want to. But at this moment, I think we have more than over 1.5 million electronic drivers in the field working and supplying energy to the UV sources. And I want to talk a little bit about how to even further improve the efficiency of the UV sources. Several years ago in Sydney we had a talk and about improving the lamp drivers for optimum powering the UV source in the most efficient way, and showed you already there that the low pressure lamps have about somewhere between 30 but even up to 40% efficiency. DBD lamps, most of them commercially seen much lower than even the 40%. LEDs at that time were up to 4%. 6 years ago, and now they are up to 7.5%, which was in a recently published report on July 18. So there's still some work to do, and I said if you want to be a sustainable system, I think the LEDs has to kick up the wall plug efficiency and should be above the 35% before it's really interesting. Now let's look to the low pressure lamps. This is a graph showing you the UV efficiency as depending on the frequency of the signal to power the UV lamp. First of all, you see that there's efficiency going down at lower frequencies, but then there's a sweet spot which is around 30 to 60 kilohertz, and most of these drivers are now applied with this kind of frequency. But we think that there's even around 5% improvement if you also optimize the waveform how you drive the UV lamps. Now, these four areas, A, B, C to D, are a little bit depending on the energy and the speed of the electrons in the plasma system. I'm not a plasma physicist, so I cannot give you all the details. And I must remember a small joke on a guy that once told me that Albert Einstein once told his wife, well, my wife doesn't understand me, but that's something different. So these four areas are a little bit depending on the frequency, and has first of all the first low frequency has depending of the time constant of the ambipolar diffusion, because that's the way how most of the energy gets lost when this ambipolar diffusion hits the tube wall and then ends it. So that's also close to DC. Then the efficiency goes down again with the lower frequencies. Has to do with the time line of the lifetime of the excited mercury atoms. Then the sweet spot, 30 kilohertz, 60 kilohertz, that's the range of where we have the maximum energy to the electrons to join the mercury atoms and give the UV intensity. Further increasing of the frequency, well, that doesn't matter because that energy doesn't help. It just confuses the electrons and recombine, and it doesn't matter, it will not help. Now, if you look to the sources to power UV sources, you will see that normally you can have a nice sine wave. In practice, you don't see that. You will see distorted waveforms. That means it's not only the sinusoidal waveform, but a lot of higher frequencies are added to that signal, and come back to that later on. But first of all, how we can see that at the UV lamp. Normally, if you start up a low pressure UV lamp, it runs up to the maximum power, here given by the point P, but after that it always goes down the UV efficiency because of a lot of effects. I come to that later. If you look to the time after the maximum power point P, very important point is the lamp temperature. You know, and I saw that yesterday also on one of the explanations from Light Tech. There's an optimum in temperature on the UV output. Too low temperature is not good, too high temperature is also not good. So that has a big impact on how that level will shift. Lamp current is important, it affects the plasma stability, but also the operating frequency. We have seen this already a sweet spot between 30 kHz and 60 kHz. But again, and we wanted to investigate that furthermore, how is the waveform of that signal impacting the efficiency? And of course, lifetime of the lamp is also important. So how can you investigate the efficiency of the waveform? So we had a lot of thoughts how to do that. You can take several electronic lamp drivers and compare them, but there are so many parameters that are different, like the operating frequency and so on, power regulation, current control. So we came up with the following setup. We just have a free programmable generator, so we could have a fixed frequency around 40 kHz in this case, and we can change the waveform of that signal. So adding a lot of high frequencies, the higher harmonics to it. But then how to power a lamp? You need some power to do that. So we did find this AE Tech RON power supply. We could lend that one from the US company. It's about 5,000 watts, a bandwidth of up to 250 kHz. So we said, well, if we do some measurements around 30-40 kHz, that would work. Then I have a Yokogawa power analyzer. You need it because sometimes you see customers that wants to measure the power with a very simple fluke equipment. Well, that doesn't work because of the frequency, 50, 60 kHz. You need some very specific equipment to do that. At last, we had one issue: how to start this lamp. So called some colleagues, and they came up with a solution. Plastic material for the high voltage test for that, and that works very nice. We could just fire it with a 5-6 kilovolt pulse, and then the lamp would ignite. So we did the first test. On the left side, you see the signal was almost a pure sinusoidal, and then we changed to a triangle shape, and we kept the power to the lamp almost constant to 175 watts and the frequency around 31 kHz. And there you see with the sinusoidal signal we had about almost 3% more UV output. Well, I think that's great. You even can further improve the efficiency of the lamp. Well, we have some good R&D guys that also always want to stretch the tests that they are doing, so they came up with a very strange waveform to put a lot of high frequency in it. Let's see how the lamp will perform. Well, we saw it was again lower at the right side, but then during this test, following happened, we saw smoke from this power supply. So end of testing, which was a pity of course, but that was just I think 2 weeks ago. So we run out of time a little bit before this presentation. So we came up with an alternative plan, and what we did is, well, we have some power supplies here, also competitor or colleagues, whatever you want to name it, and of course our own electronic drivers. What you see here is that we have a nice black box where we can put in the lamp. We have an additional ventilator with it, so we can control the temperature to some content to keep the temperature of the lamp constant. You see the UV data logger on there, every time the same fixed position. And then we had the device on the test, we had an oscilloscope to it, and of course the power measurement on the primary input, and did the tests. So here you see two different pictures. On the left side you see the Nedap driver, in this case it was the Unimulti driver, and set at constant current to the lamp. And on the right side you see one of the other European supplier, and the green signal, that's the voltage applied to the lamp. There you already see it on the left side, on the bottom. That's for you analysis, so it gives you the amount of high frequency signals in that almost sinusoidal shape. There you see only 3 measurements. Ground frequency, in this case that was, let me see, about 50 kHz. and two other points. And with the, well, I call it almost triangle shape, you see that there's a lot more high frequency in that content. And if we zoom in later on, and once again want to say that we used or regulated both to the same, or Nedap drive to the same current. Difference is about 0.5%, where the driver B is slightly higher, but within 0.5% of the current, and the lamp powers approximately 330 watts. If we zoom in, there you see on the Harmonics that the base frequency is 40 kilohertz, but you see that we even see frequencies up to 755 kilohertz, which is a reasonable good amount, and that gives you a distortion value. I did some calculations, but I think it was around 23 or 25% on total THD. And when we did the same test, we saw, in fact, almost the same value or difference in values between the test we did with the oscilloscope or with the generator, the pure sine wave. And going to the peak, if we waited a little bit longer, then also thermal issues came up, so we didn't test too long. But overall, the minimum surplus was about, again, 2.9, so almost 3% more UV from this more sinusoidal waveform. So the deviation from ideal waveforms, that has some impact. It has caused a nonlinear plasma response. It gives this harmonic distortion. And also we need to think about the electrodes. Electrodes can show a little bit more sputtering due to these content of high frequencies. High frequency currents tend to operate at the surface of the electrodes and causing more sputtering. So also the lifetime will be of importance. So in general we can say that if you lower the amount of THD, so the less distortion on your waveform, you can go up to 3% seen in this test. We are planning to do some more testing, to more accurate tests to show what the exact is, because also during this test we had to do something with cables and so on, which has an impact. By the way, talking about cables, looking to the total efficiency, I want to add a few things. Because we're all trying to make these systems on UV most cost efficient, so get it more efficient, that the wall plug efficiency is as high as possible, because energy is getting more expensive in Europe, in the US, everywhere. And by the way, we need the electricity power to load or charge our cars nowadays. And in the Netherlands already we have a problem that there's not enough capacity to start up new factories or new homes. I know that some people have to wait for 1.5 years because there's no electricity available for them. So looking at the total efficiency of the system, most people think, well, we have the lamp driver. Most of the time we want to have a cable of 20, 30. Sometimes people ask me, can we have 100 meters between the lamp driver and the lamp? I say, yeah, you can, but it's not a good system. Lamps will not always ignite and you lose a lot of energy. Because it's not that cable, it's an inductance, it's a capacity and resistance between the two wires on the filament, but also between the electrodes. So there's a lot going on. And using this, especially on the left, on the top, the problem is that with higher frequencies, the current is not going through the complete wire. It is just going to the outside of the current. So the magnetic fields force the current to go out. Even at 400 kilohertz, it's only a small part of the wire that's carrying the current. That means that the impedance or the resistance of that cable is going up dramatically. So we see that roughly, compared with standard cables that we have seen in the field, it's sometimes between 2 or 3 times a higher resistance during this frequency. And, you know, we want to use this frequency because we know that there is a sweet spot, 60 kilohertz or 30 to 60 kilohertz on those lamps. So we need to take care of that and taking the right wires. And what we always see on the bottom, also take non-magnetic material, because then also the eddy currents kick in. So you can see there the same wire between high frequency and low frequency operations. So don't use any magnetic materials in your system. Going back to my presentation in Sydney 6 years ago, I talked also about, this is what we call now is the supply voltage to the lamp, but also the supply voltage to your driver is very important. And it's also valid for LEDs or any kind of sources that you're using. The THD, the distortion on the mains voltage, is also of a very high importance, and also the power factor. So keep the voltage and the current nice in phase. We did a test some time ago. This is not a disinfection project, but a curing project where we used the same UV to dry inks and paint. It was a big printing machine, up to almost 130 kilowatt system, only on UV. So every station is one color, using about 20 kilowatts of power on UV. I must say with medium pressure lamps running approximately 4,000 hours. And there you see the difference between Nedap, where we have a very high efficiency, a very low distortion, THD, and a very high power factor. And there you see that the energy consumption can be, much more better if you take the right decisions and have the right specification, and saving almost 9.8% of energy, which is a lot. So, in total, if you look to what you can save at the power line, because these losses are just generating heat, and by the way, nobody is paying for that, because the energy the companies that produce the energy don't like it, supplying something that nobody's paying for. And also on the driver, lamp cable, but also in the waveform to the lamp, you can save a lot. So there's a possible saving of 11 up to 23%. And I think it is very important to keep that in mind, to optimize it. So that we can say that the wall plug efficiency of low pressure lamps can be up to 40% now and in the future. And I said there are millions of these lamps installed in the future. And I think the only way, in the future we will go to LED solutions. But I think for the coming 10 years, this solution is still one of the best and the most cost efficient if you look to the energy consumption. As now, we still need 500% more energy to drive these systems with LEDs. Then I want to thank our colleagues, Jurgen, Rudy and Patrick, and end up doing all the testing on the plasma physics, thanks to Alex Ronner from Accelerators, who was a great help, and of course the guys from EET for the UV sensor. And thank you for your attention. Maybe you have any questions.